Chapter 1.2, Finding Limits Graphically and Numerically. In this section, we will do the following things. We will estimate a limit using a numerical or graphical approach. We will learn different ways that a limit can fail to exist. Another topic that's in this section that is important to know about, but we're not going to do, is to study and use a formal definition of limit. And you're going to see something called this epsilon delta definition. So when you see those in the questions, you may ignore those. First off, what is a limit? You guys are familiar with the value of a function, which is the number that comes out of the function when you plug in a certain number. Well, a limit is like that, except this is the value that a function approaches. It's not what the function becomes. It's what the function approaches. A lot of times you're going to find that the limit and the value of a function are the same. First example. Suppose you are asked to sketch the graph of a function f given by f of x equals x cubed minus 1 over x minus 1, where x is not equal to 1. Well, first off, you cannot graph it at 1 because that makes the denominator 0 and we cannot divide by 0. So let's take a table of values and see kind of what it looks like. Do plug and chug for a couple values. We see that at 1 we have no value. But if we look from left to right, on the right side, what's happening, these numbers get closer to 3. And on the right side, these numbers get closer to 3. So even though we cannot put 1 into the function, we can approach 1 from the left and from the right, and we can see that the limit of the function is 3 because it gets closer and closer to 3. Let's take a look at this graphically. We can see the same thing. We have a parabola with a hole in it. And that hole happens at 1 because you cannot divide by 1 in this problem. And the number where it would be is at 3. So what we say is that the limit of our function as x approaches 1, let me repeat that, the limit of our function f of x as x approaches 1 equals 3. Okay. Let's look at a numerical approach to this. All right, so we have a table here. Find the limit as x approaches 2 of x squared minus 3x plus 2 over x minus 2. Now you can take a look at that and we can see that we cannot just plug 2 in and get a value because you can't divide by 0. So let's take a look and let's do this in our graphing calculator. Develop a table in our graphing calculator. So let's put that function into our graphing calculator. Y equals x squared minus 3x plus 2 divided by x minus 2. Let's look at this table of values. I'm going to start by plugging in the numbers into the table that they give us. So I need to change my table settings. Second table set, I'm going to change my independent variable, which is the x values, to ask. So I can type in any x values I want. I'm going to go look at the table. So the first x value they want is 1.75. And as I do that, I see it's 0.75. And then we'll go 1.9. Then we got 0.9. Continue typing in those values. There I got the left side. Now 2 we know won't work. It'll say error. So there's my left side. my right side, do the same thing here. So 2 does not work, but 2.001 does. 2.01 does. 2.1 and 2.25. So as I evaluate here the left and the right sides, I can see on the left side my function appears to get closer and closer to 1. And on the right side, my function appears to get closer and closer to 1. So what I would say then is that the limit of this function is 1 because the left side and the right side both get closer to 1. The next example, evaluate the function f of x equals x over x squared, the square root of x plus 1 minus 1 at several points near x equals 0 and use the results to estimate the limit. We'll do this in the table again. And again, we'll do this with the graphing calculator. We'll enter our function, x over, group the bottom, the square root of x plus 1 minus 1. And they wanted to know near 0, and the reason they wanted to know that is because if I put 0 in, we can see we get an error. So what I want to do is evaluate a couple on each side of 0. So I'm going to start with negative 0.1. I'll try negative 0.01. Let's do negative 0.001. Let's do a little bit on the right side. We'll go 0.001. We'll do 0.01. And we'll do 0.1. And as we look at this, we can see that on the left side and the right side of 0, we seem to be getting closer to the same number. And that number is 2. So we would say the limit of our function, or you could write out the function as x approaches 0 equals 2. Let's look at this one. Let's look at this one graphically. Now if we take a look, this is a piecewise function, which means you need to consider each piece separately. And we can see that our separation is at x equals 2. And x equals are not equal to 2. So we can see that when x is equal to, our value of our function is 0. So at x equals 2, we'll have a point at 0. Every place else, when x is not equal to 2, our function will be 1. So we take and we sketch a quick graph. Now as we look at it, as we go, we get closer and closer from the left side. What number do we get closer to? And as we get closer and closer from the right side, what number do we get closer to? Not necessarily what number is the function, because the function is 0 at 2. As we get closer and closer to 2, what number is the highlight from the left and right getting closer to? Well, it's getting closer to 1. So what we would say is the limit as x approaches 2 of our function is 1. Because that's the numbers we get closer to, not necessarily the numbers that it is. When do functions fail to exist? There are 3 times that functions fail to exist. First, if something happens that's different from the left to right. Second, anytime there's unbounded behavior. And third, anytime we have oscillating behaviors. What do each of these mean? Well, different from left to right. You've kind of seen me talk about what is approaching to the left, what is approaching to the right. Well, if it approaches something that's different each time, the function does not exist. We cannot approach -1 from the left and +1 from the right and have a limit. Unbounded behavior. In this function, you're used to this function, 1 over x squared. The function increases without bounds. This limit does not exist because it keeps getting higher and higher and higher as we go. So we would say this limit, as x approaches 0 of 1 over x squared, you can say does not exist, or just write DNE. And the final time when a limit does not exist is oscillating behavior. Example here, sine of 1 over x. As you get closer and closer to 0, what's going to happen is your function is going to oscillate between two numbers. Let's take a look at this function numerically. We got the graph there. So if we go to y equals, enter in sine of 1 over x. And just make sure you are in radians. In our table, we can see that we're at 0.5, 0.5, negative 0.8, 0.8. If we were to get in even closer, let's do negative point, let's do 3 zeros. Now we're at 0.3. If we do 4 zeros, then we're at negative 0.03. You're oscillating between -1 and 1. So, in summary, a limit is a value a function approaches, and there are 3 times a limit does not exist. If it approaches 2 different numbers from the left and the right side, if it increases or decreases without bounds, or if it oscillates between 2 fixed values.